Welcome to this Chat Physics Live session on using geology in your physics classroom or Physics Rocks. I'm Alex Inchenko. I'm a secondary GCSE and A-level physics teacher, but I previously trained as a geologist and worked in the oil industry, and I love trying to put as much geology as possible into my physics lessons. So first of all, why even use geology in physics lessons? Rocks are really tangible. You can feel them, you can hold them, you can touch them, and students can see them around them if they're out and about in the countryside. They illustrate that physics phenomenon can be seen in the natural world and everywhere around us. And the UK has greater geological variety than any other country of its size, but yet we don't really see geology cropping up very much in UK curriculums or specifications. Now, it would be absolutely fabulous if we all could take our students to Guatemala to see the volcano in this picture, which is Pacaya, which can show us some amazing flow dynamics, earthquakes, and other physics phenomena. However, that's probably not realistic, a little too dangerous, and a little too far. So I'm going to talk today about some of my favourite ways to use geology in the classroom, with a particular focus on minerals and light. Minerals and light link really nicely into the curriculum whenever we're talking about absorption, transmission, refraction, reflection of light, electromagnetic waves, energy levels in atom, or polarisation of light waves. So most of the things I'm going to talk to you today about are suitable for Key Stage 4 or Key Stage 5, but hopefully if you teach younger students, you'll also pick up some things that you might like to use in your classrooms. Firstly, looking at fluorescent minerals. You may have some examples of fluorescence that you commonly use in your classrooms, such as the security markings on banknotes or looking at tonic water. But fluorescent minerals have immense variety. They're really interesting and a little bit different to look at, and they're clearly not man-made objects like our banknotes. The two pictures in front of you are from a display at the Natural History Museum in London. They show examples of fluorescent minerals. The pinkish mineral on the left is fluorite, which is one of the best known fluorescent minerals. It's well known for fluorescing in a blue colour, but has one of the biggest ranges of fluorescence of any mineral. The early study of fluorescence involves some of the big names in physics, with the phenomenon being first discovered by Sir John Herschel in 1845, and he noticed it in a solution of quinine, which we know much better as tonic water. The first published studies of fluorescence came shortly after that with Sir George Stokes' 1852 paper on fluorescence in minerals. It's got a great title, On the Change of Refrangibility of Light. It's actually quite an easy read. You could easily give sections of it to your students to read, and it's freely available from the Royal Society's website. He was the person who coined the term fluorescence, which is named after the mineral fluorite. This is our school collection of fluorescent minerals. I've laid them out on black cards so that we can see the fluorescence more successfully. However, in order to properly see fluorescence under UV light, I'm going to have to turn the lights off. I've turned the lights off so we can get a really good look at these fluorescent minerals, which are fabulous in UV light. However, the camera's not quite picking up the colours properly. So these are mainly come in pinkish colour fluorescence, although our fluorite is more of a blue colour. It does look pink on the camera though. And I'm going to show you some zoomed in photos of the fluorite and the black amber. Focusing on the fluorite, you can see that whilst the whole specimen fluoresces, there are some dotted patches where we've got a different chemical composition, where the fluorescence is darker, more intense, and more purple. Whereas the black amber displays both green and purple fluorescence, and this can be seen in these beautiful stripes and patterns throughout the specimen. Fluorescence is very common, occurring in around 10 to 15% of all minerals. It normally occurs due to the presence of an activator mineral within the crystal structure, such as chromium, iron, or manganese. Electrons in their ground state will be excited to a higher energy level when UV light is incident upon them. So if we put UV light in, if the electrons were to fall straight back down to their ground level, the light emitted would be exactly the same frequency and the same wavelength as the light that was put in, and this effect is called luminescence. In order to get fluorescence, we need a little bit of thermal loss of energy to produce a slightly lower excited state. Let's call this one over here E1, and we've got our second excited state. Now when it falls back down to its ground state, it will emit light with energy E equals HF. And the frequency will therefore have to be lower, which will make the wavelength longer, and the light will be in the visible spectrum. If you'd like a virtual museum visit to see some fluorescent minerals, or just want some great images of fluorescent minerals, then Google Arts and Culture have an online exhibition from the Brooklyn Children's Museum. This exhibition involves lots of wonderful examples of fluorescent minerals and includes some specimens from the UK, which you could definitely have students try and locate on a map. I'm sure some of you watching this will live in areas near where some of these have been found. Another feature of minerals, which I particularly like to look at with my A-level students, but it's also fun to look at with younger students, is birefringence or optical anisotropy. This is sometimes called double refraction. If we look through the calcite blocks in the diagram, we can see that all of the grid lines appear to be doubled. This is because calcite has a crystal structure where light does not travel at the same speed in every direction. As light enters the crystal, it's split into two directions according to the crystal structure, and each of these directions has a different refractive index. Calcite's kind of fab because it's really easy to see the crystal structure on minerals of calcite. One of the best ways to see the effects of birefringence in minerals is to look at thin sections under a polarising microscope. A thin section is a piece of rock that's been ground down until it's 30 micrometers thick and transparent to light. A polarising microscope uses plane polarised light, i.e. light that's polarised in one direction, and it has a second polarising filter at 90 degrees to the direction of the first polariser. So if a mineral has no structure to it, it's the same in every direction, it will appear black when you've got both polarising filters in. However, birefringent minerals change the direction of polarisation of light, as well as having light travelling in two different speeds through the mineral. When the light rays hit the second polarising filter, they're recombined, and the path difference between the recombined rays of light will give us the effect of producing interference colours. This chart shows us the different interference colours that can be produced. On the left-hand side, we have the colours where there is very little to no path difference between our two rays of light, and as we go to the right, we increase the path difference between those rays of light. I'm now going to take you to the lab to show you how to build your own polarising microscope. So here I've got a bit of a make your own polarising microscope kit that your students can do. I've got a biology just standard lab microscope, 2 pieces of Polaroid filter and some rock thin sections. Now these rock thin sections are not very interesting on their own. With the naked eye they just look like translucent minerals. They get a little bit more interesting if we put them under the microscope. We can see colours then, we can see crystal outlines. But really what we want to do is we want to see the effects of birefringence. Therefore, we need a polarising microscope. So first of all, you need to check your polarising filters are at 90 degrees to each other. And a typical polarising microscope would have one filter above the light source. So let's pop a filter there. If you're not able to put a filter above your light source, you can put the filter straight on the stage. It would also have a filter between the eyepiece and the lens. Now, we can't put the filter in there, so what we'll do is instead we'll put our slide on the stage and we'll put our filter on top, just making sure that this filter here is at 90 degrees to the filter below. Now, if you look down your microscope, you should see some really interesting effects. As you can't see what I'm seeing down the microscope, I'm going to take you over to a virtual microscope demonstration. This is the Open University's virtual microscope software. There are a couple of different virtual microscopes out there which are all free to use. This one I personally like, one because I've got one of my favourite rock specimens in front of me. I have a metamorphic rock, so you can choose your category down the side, which is a schist. This one in particular is a garnet mica schist. If you don't know anything about geology or minerals, there's a nice little cheat sheet on the side. So if you click on the names of one of the minerals, it will zoom in and take you to that mineral in order to help you identify it. So I could also zoom into a garnet. If I want to look in a little bit more detail than I can see in this whole thin section, all of these numbers will provide me with a microscope image. So let's look at number 1. On the left-hand side, we've got our view in plane polarised light, and on the right-hand side, our view between crossed polars. You'll notice that we can't see a lot of colour in plane polarised light, even though we know our minerals are coloured. This is because they're cut so thin and so much light is passing through. But you might be able to see here the chlorite has a greeny tinge to it. And if you squint, you might believe the garnet has a reddish pinkish tinge to it. However, when we view the mineral between crossed polars, we see something very different. This is where we see our interference colours. So the micas down here have these high order interference colours. So they're quite bright but washed out. And this is because mica is highly birefringent, so we get a large path difference between our rays of light passing through. If I turn the stage, we'll see that the garnet remains darkened at whatever angle we place our thin section. This is because garnet is an isotropic mineral, so its refractive index is the same in all directions. If you'd like to add a little bit of maths to this, there's a nice question on birefringence on Isaac Physics, which looks at a quartz crystal and its different refractive indices. Now, I've just touched the surface of what you can do with geology and physics lessons, looking at the particular examples of minerals. If you'd like more resources and ideas, head to some of these sites. Earth Learning Ideas is loads of practical activities. A lot are linked to the GCSE and A-level geology specifications, but they have things that are relevant to all science lessons at all levels. IRIS is the Institute of Research in Seismology, who have a really good section on videos for use in lessons and teaching. There's a link there to the virtual microscope and a link to the Open University's Introduction to Rocks and Minerals course. If you wish to purchase your own rocks and thin sections, you can head to any of these places. The fluorescent minerals that I showed you were from Geology Superstore and they cost only a couple of pounds each. The more expensive thing to buy is actually a UV torch. You might already have one, but check if the UV torch you have is long wave or short wave. Most fluorescent minerals respond best to short wave. Thin sections do tend to be a bit more expensive, so do ask your local university earth science department if they've got anything they're throwing out. People who work as petrologists usually use thin sections. Mine, for instance, you will notice do look rather old. That's because they are. They were found at the back of a cupboard in the Natural History Museum and hadn't been used in many, many years. Thank you for listening. I hope I've inspired you to add a little bit of geology into your physics classroom. And if you'd like to find out more, don't hesitate to get in touch.